And we know that Q has a simple zero. If Q has a simple zero, then the residue. Okay, good morning, everybody. So, there is one important announcement I have to make, and I'll definitely also send it by email. But there is now a relaxed university policy on the S/U grading. So S/U means satisfactory/unsatisfactory, and usually it takes some effort to switch to this kind of grade because typically the university wants you to get a letter grade. But because of all this coronavirus stuff, it's now automatic. So if you think you won't be satisfied with your grade, you can switch to this S/U, and then, well, unless you're doing very badly, you'll get the satisfactory grade, and nobody will know how well you actually did. So it's completely up to you. You can stay on the letter grading, or you can switch to the satisfactory/unsatisfactory. So it's for you to choose, it's for you to decide, but if you want to switch, then you will be allowed. No questions asked. Okay, so I'm still thinking about how to run the final, not because I think I'll have some proctoring issues, but mostly because I just want to do it in some more relaxed way to mitigate all the damage this virus is doing. So I'll let you know as soon as possible. But so you are turning in your homework today, and as I emailed, all homeworks after that will be mostly extra credit, so you'll be able to bump your grade. I'll probably assign some mandatory problems, just like the ones that are super important, but the rest will be extra credit. Okay, so let's now start. And sorry, I want to turn a timer on. Great. So, okay, so I want to remind you this definition that the principal value of the integral, so here it is by definition equal to this limit. Now, I want to erase all this because I was in a hurry and it kind of wasn't really good that I didn't give any example. So I want to give a very important example here. An example that shows how principal value can actually make a difference. So let's compute this integral. And as you hopefully remember from Calc 2, this integral has no way to converge in the like regular sense. So this integral without the PV diverges badly. Because so if there are two problems with minus and plus infinity, then we should split it in two like this. And this thing is already plus infinity because x has an antiderivative and it's x squared over 2. When we plug infinity, we get infinity. So what happens with the principal value? So for the principal value, and this will be very surprising and very anti-intuitive. For the principal value, we don't split. Like we treat these two problems together, and that's very important. So we write an integral from minus r to r, and then we send r to infinity. Okay, so now there is an antiderivative. Sorry, I don't need the integral anymore. I need to write x squared over 2, plugging the limits. And then when we plug the limits, we get r squared over 2 minus r squared, minus r squared over 2, and that's 0. So this thing is 0, and so the limit is also 0. So despite the fact that the integral diverges, it turns out that the principal value is really well defined and there's no problem. So principal value makes more integrals convergent. On the other hand, so I'll state the fact, it's not hard to prove. We know that if the integral, whatever, I'll do from minus infinity to infinity, f of x dx, and that's a real valued integral, not a complex, converges in the calc 2 sense, then it is equal to the principal value. So if it converges nicely, then it's all the same, but if it diverges, then the principal value can actually help it to converge. Okay, so now let's do a real example. Now, here is a warning. This will be a multi-step example. So I'll try to do many examples because it gets harder. Well, already last time we had some examples, what we do. We factor out, then we differentiate, then we do power series. So it only gets worse. Okay, so now step number 1 is that I want to transform it to an integral from minus infinity to plus infinity. As of now, there is no reason for that. So I cannot really explain you why, except that I know that it will work. But as of now, we keep in mind this kind of contour. And because it's minus r and r, it should be from minus infinity to infinity. So how do we do it? Well, we see that this is a even function. Okay? So that's an even function. So it's 0 at 0. Then, well, I have no idea what it does. It probably increases and then it decreases back to 0. And here it does the same. So we are computing this integral. Okay? So we know that the integral from minus infinity to 0, f of x dx, is equal to the integral from 0 to infinity of f of x dx. And this is because it's an even function, so this shaded area is equal to this area. And so this implies that if we just integrate from minus infinity to infinity f of x dx, we'll just need to double this integral. Okay, and therefore to compute this integral, we can compute this integral and then divide the answer by 2. So what we need is 1/2 times this. Now let's suddenly extend f to the complex plane. So last time I tried to show you something about sine, and sine was extended in a weird way. So instead of sine of z, we wrote e to the we wrote e to the ix. So here it will be more straightforward. That's a better example. We can realize that instead of x, we can just plug any complex number, except that this function over here, f of x, it's a really decent function because the denominator is never 0 for a real x. This function f of z is not so decent anymore because occasionally the denominator is equal to 0. Okay, and now let's draw this contour. So I want to integrate f over contour c. But I also want to index c by r. So cr is this. finally I'm drawing this picture in a meaningful example. Okay, so this is a circle of radius r only above the real axis. So we go counterclockwise, and then as soon as we hit x-axis, we return to this point via this horizontal path. So CR consists of two parts, and remember that we sort of worked hard to explain why we can integrate over these not always differentiable curves. Alright, so we know that this integral over C sub r is 2 pi I times the sum of residues inside the contour. So let's count how many residues do we have. Okay, so we have residue z equal to I, and then we have several more. So we in fact need sixth root of -1. So the residues are at -1 to the power 1/6, because this is what produces the residue. Okay, so we know that -1 is e to the pi I plus 2 pi n, so -1 to the 1/6. I'll just list all the values. So pi I over 6. So pi I plus 2 pi n is 3 pi I divided by 6 will be pi I over 2, which is I. Then 5 pi I over 6. Okay, then we add okay, 4 pi n, then we add 6 pi n, so we get 7 pi I over 6. Then we add 8 pi n, so we get 9 pi I divided by, sorry, I here. Hopefully you caught this, but uh, all listed values here are correct. I was assuming I is there. Okay, so we add 8 pi I, we get 9 pi I divided by 6, we get 3 pi I over 2, have 1, 2, 3, 4, 5, I need one more. So 10 pi I, get 11 pi I over 6. So which ones are residues? Well, e to the pi I over 6 is somewhere here. Then the next one is this, the next one is this. Let's draw a picture again. So one is here, another one is here, another one is here, and then another one is here, and here, and here. So these ones are residues, and these ones are not, because they're not in the contour. So only these three friends are residues, and these are not. Okay, so now I can actually compute the residues. And now I'll go a little bit back to remind you the fact that if we have P over Q, and we know that Q has a simple zero, if Q has a simple zero, then the residue I had it earlier, hopefully. Yeah, here it is. So if Q has a simple zero, then the residue is just P of z0 divided by Q prime of z0. Here it is. Okay, so what do we know? I'll actually go ahead and compute it here. Oh, and sorry, I promised that I will hold my iPad horizontally. Well, let me start now. I'll then go to the next page. Flip it. You know what? I'll start the recording because I'm afraid that YouTube won't like it. So hang on. I'll start the recording and I'll start the stream. plus 1, and I need to compute my residues at 3 points. Okay, so the residue at e to the pi I over 6 will be z squared divided by the derivative of the denominator, 6z to the 5th, plugging this. And okay, so z squared cancels out, so I got 1 over 6z to the 3rd. I need to plug this, and when I plug this I get 1 over 6, and now I need to raise this to the 3rd power. So e to the pi I over 6 cube, 3 cancels out, I get 1 over 6 e to the pi I over 2, and pi I over 2 is I. So 1 over 6 I, let's multiply by I, it will be minus I over 6. That's the residue at e to the pi I over 6. Okay, so the residue at e to the pi I over 2 is the same, z squared divided by 6z to the 5th with this substitution, and it will be 1 over 6 e to the 3 pi I over 2, and 3 pi I over 2 is minus I. And this will be I over 6, and finally the residue of f at e to the 5 pi I over 6 is 1 over 6, and now I need to raise this to the 3rd power, so e to the 5 pi I over 2, and 5 pi I over 2 is again, e to the 5 pi I over 2 is again I. So minus I over 6. And so we know that the integral of f over CR is 2 pi I times sum of the residues, so minus I over 6 plus I over 6 minus I over 6. All these fellows disappear. I get, so 2 and 6 cancels out, and I times minus I is plus 1. So what I get is pi over 3. Now that's really nice. Why is this nice? Because, well, I know, well, it's probably a bad way to check the answer right now. Oh, actually, turning the screen didn't hurt, it rescaled. So I'm integrating this f, and it's non-negative, so I know that I need to get a non-negative answer. Like, I'm not allowed to get a complex answer at the very end because I've started the real valued function. Well, this pi over 3 brings me closer to a decent answer. Okay, now, so this was the practical part. Let's do some theoretical part in this problem. So I'll split this integral into two. One is this, only over the semicircle, and another is this. I'll leave the first one alone for a while. And the second one I'll parameterize. So this has a parameterization gamma of t is equal to t. Okay, because this horizontal line stays on the real axis, and t is from minus r to r. So gamma prime of t is 1. And so here I just get f of gamma of t, which is f of t, times gamma of t prime 1 dt from minus r to r. And this is exactly what I want eventually. So what do I have? And this left-hand side is pi over 3. So here is my result. Pi over 3 is equal to the integral of f of z dz over this arc plus the integral from minus r to r. And I have f of t, but I can easily change it to f of x dx. Now let's pass to the limit. Okay, so I want to pass to the limit as r goes to infinity. Well, the left-hand side is a constant. Okay, like I have absolutely no concerns about the left-hand side. Left-hand side always stays power 3. That's pretty cool. I'm integrating f over this contour, which becomes bigger and bigger, but it still has only these 3 residues, and so the result never changes. Well, that's not very surprising by now. We by now so many examples when we have different contours, but the results are the same. Okay, so hopefully this will be true. So limit of this, and remember that this arc depends on r, plus the principal value. Okay, because when I put the limit right here, I get exactly the principal value. Now, I want to say that the principal value is equal to the actual integral. Why is that? Because look at our function again and recall your Calc2 class, and then you'll realize that by the comparison test, this integral converges. You compare it to something like 1 over x to the fourth, which converges at infinity. So principal value is in fact equal to the actual one. And now I'll do something that, okay, I don't need principal value anymore. I'll do something that would be horrible if it wasn't like true always. So when we use this contour, we always keep in mind that this first limit must be 0. So there is no good way to compute this integral unless its limit is 0. And now we will prove it. And unfortunately, the only way to prove it is to recall our estimate of integrals. So let's recall, how do we estimate an integral? It's less or equal than the maximal value of f on C times the length of C. Okay, so let's apply it for C sub r. Well, we know that length, so it's a semicircle. The length of the full circle is 2 pi r, and the length of the semicircle is 2 pi r divided by 2, which is pi r. So this is a huge thing actually. When r goes to infinity, this goes to infinity. So our only hope is that f will be super small, and fortunately it will. Why? Because we have this. So what's f? Well, f is this. So let's write it like this. So this whole thing about estimates of the integrals was not for nothing. It was for this residue stuff. Okay, so we're on C sub r. So absolute value of z is actually r. That's not even an estimate yet. So I need to estimate this denominator. So I'll estimate it keeping in mind that z is huge. So z is on this semicircle of radius r. And I need to estimate it like this, because eventually I want to get this kind of estimate. I want f to be smaller than something. So for the fraction to be smaller than something, I need the denominator to be bigger than something. So how do I estimate absolute value of something is bigger? Well, I need to write the difference of this and this, or the other way around. But because z is huge, I'll write it this way. And z to the sixth absolute value is the same as absolute value of z to the sixth, and this is r to the sixth minus 1. So eventually, this fraction is less or equal than r squared times r to the sixth minus 1, which implies that the integral over cr f of z dz is less or equal than the maximal value of f, which is this, times the length of c, which is pi, so pi goes before the fraction, r cubed divided by r to the 6th minus 1. And this is a very small thing when r is huge. R to the 6th completely destroys r cubed. So this implies that the limit of the integral over CR of f of z dz, even with the absolute value, is less or equal. Okay, so the integral is less or equal. So the limit is less or equal than the limit of this. And hooray, hooray, this is 0. So the limit of the absolute value is less than 0. How can this be? Well, only if the limit is actually equal to 0, because absolute value is a non-negative thing. So limit of the absolute value is less than 0 implies that it's equal to 0. And therefore, so what's the big conclusion? So we had this line, these two lines written. So we have pi over 3 is equal to what we want, plus this limit which is 0. And so the conclusion is that pi over 3 is equal to the integral we needed to compute. Well, we actually needed this integral. So that's pi over 6. We need to divide the answer by 2. So that's an example. Unfortunately, so I know you'll never believe me, but this is sort of the easiest possible problem on this application of residues. They're all, well, we won't dive deeply into hard ones, but this is kind of not considered to be a hard problem. Well, I mean, I understand that it's hard, but from within this section, it's sort of a basic problem. So every problem the application involves something like this. So I just want to call your attention to the fact that there's no good way to compute this integral without residues. So I encourage you all to try to come up with an antiderivative, and you'll see that you're running into problems. It might be possible, although I'm not sure, but it's it will be pretty crafty anyway, and I'm actually not sure it is possible. All right, so let's do another example. I'll go ahead and do a couple of examples from the exercise section, because I think that one example is certainly not enough. You need to see more. Okay, let's do, for example, this. Now, for example, the book really likes these even functions. I don't know why. X squared plus 4. So here you probably can integrate without residues. You can do partial fractions, and if you do partial fractions, we'll just have two arctangents. It's actually not so hard to do if you mastered partial fractions and haven't forgotten them yet. But we'll see that with the residues, it's also not super hard. Okay, so first of all, because it's an even function, we know again that the integral from 0 to infinity is the same as 1/2 times integral from minus infinity to plus infinity. So then we'll use the same contour as before. So the same CR. So CR is everything here. And so we have f of z is equal to z squared divided by z squared plus 1 times z squared plus 4. And we know that the integral of f of z dz over CR is 2 pi I times sum of residues. So what are the residues? The residues are plus or minus I and plus or minus 2i. Here actually the residues are not such a big deal. So which ones are in CR? Well, here is I, here is 2i, here is minus I, here is minus 2i. Well, these are not in CR. We only need this one and this one. Okay, now the only tricky thing is to write P and Q correctly. So again, we see that these poles are of multiplicity 1. So it shouldn't be like super hard to find the residues. However, it will become a little bit more complicated if we choose like this P and Q incorrectly. So let me write F like this. And this thing will be my P, and this thing will be my Q. So P of I is not 0. Okay, P of I is not 0, and Q of I is 0 and multiplicity 1. So this means that the residue of F at I is equal to P of I divided by Q prime of I, and P of I is what? It's minus 1 divided by minus 1 plus 4, and Q prime is 2z, so 2i. So what's this? So this is minus 1/3 divided by 2i. It's 1 over 6i. Okay, and now I'll write f of z like this. Sorry, I'm using this slash in different ways, but anyway, now this will be my p, this will be my q. So the residue of f at 2i is p of 2i, which is minus 4 divided by minus 4 plus 1, and q prime is 2z, so 4i here. So it's minus 4 divided by minus 3. It's 4/3. 4/3 divided by 4i. It's 1 over 3i. This, by the way, was I over 6, and this is minus I over 3. So okay, so integral over CR of f of z dz is what? Is 2 pi I over 6 minus I over 3, which is 2 pi I times minus I over 6. 2 cancels out, and again we get pi over 3. It's a miracle. We don't always get pi over 3, that's just a coincidence. Okay, and so we write our formula again. Pi over 3 is equal to the integral of f over this plus integral of f over this. And the great thing is that this second thing doesn't depend on what is actually f. So this integral over this horizontal line will always be the integral that we need from minus r to r. And so now we pass to the limit, we write the limit here, we write the limit here, we write the limit here, and our final goal is to prove that this limit is 0. Well, why is that? Well, let's estimate f. What was f? I forgot what's f. It's z square on CR. Z square plus 1, z square plus 4. So I break the absolute value. You know what? I'll actually do it slower. I was going to build up on the previous problem, but maybe it's better for you to see this again from scratch. So we are now on this semicircle, and so absolute value of z is always r. And now my ultimate goal is an estimate like this. So again, I need to estimate the denominator from below. And again, z is huge. So the right way to do it is like this, big or equal here, of course. That's r squared minus 1. And similarly, z squared plus 4 is bigger than absolute value of, z squared minus 4, which is r squared minus 4. So eventually, f of z is estimated by r squared. Here's the r squared divided by r squared minus 1, r squared minus 4. Well, f of z is great, but that's not what I need. I need the integral. And it's again less or equal than the maximal value of f times the length of my contour, which is again pi r. That's the great thing. That's another great thing, is that for the same contour we have the same length. So if we had the length pi r right here, then we'll have the length pi r right here too. So what do we get? We get pi r cubed divided by r squared minus 1, r squared minus 4. So who wins? The denominator wins, fortunately, because the denominator is sort of like r to the fourth. This is the leading power, and this is the leading power. When we multiply them, we get r to the fourth. So we get something like r cubed divided by r to the fourth, which goes to 0. So the limit of this f of z dz as r goes to infinity. So that's unfortunately a super essential step. Fortunately, it's always pretty much the same. You always estimate f the best way you can, and then realize that everything goes to 0. Never ever do these integrals go to anything except 0. By the way, if you really miss L'Hopital's rule, then that's exactly the place where you can use it, because it's like a real valued one variable limit. So that's 0, and so we win. I won't rewrite it, but let's go to this formula. We have pi over 3 is in the limit, so I put a limit here, here, and here. Well, limit doesn't do anything to pi over 3. This limit is 0, goodbye, and this limit is what we need, except that we need to divide it by 2 to get the integral from 0 to infinity. Okay, so what else? Well, let's do one more. Somehow this one more will be even easier. Okay, this you can definitely do without the residues. You complete the square and you realize that it's an arctangent. So the answer, well, the answer should be something like pi over 2. Although I'm not exactly sure. It won't be pi over 3, which is nice. Or pi over 6. So let's do it. So let's draw the same contour. This I'll do a little bit faster. So this will be my CR. And which residues do I have? Let's solve this. So z is minus 1 plus or minus square root of 1 minus 2. So square root of minus 1, which is minus 1 plus or minus I. So where are they? Minus 1 plus I is here. Minus 1 minus I is here. So there is one single residue. Wow. So cool. So we only need the residue at minus 1 plus I. Okay, so f of z, by the way, is 1 divided by z squared plus 2z plus 2. So this is p, this is q, that's a 2. I need p divided by q prime. So q prime is 2z plus 2. Q prime is 2z plus 2, so here is 2z plus 2. Okay, minus 2 cancels out. I get 1 over 2i, which is minus 1 over I. Sorry, minus I over 2. And so the integral of f over CR is 2 pi I times minus I over 2, which is pi. So the answer will be pi. We already know that, because we now need to do the theoretical part, which is always the same, pi is equal to this plus this, and the second one is the one we need. And now I need to estimate f. So it's 1 divided by this, and this is going to be a little bit trickier. But the plan is the same. We need this. Okay, so first of all, let's get an expectation. Which term is helpful? Well, this one, because when z is huge, then z square should beat all the other ones. So I really don't care too much about 2z and 2. What I care about is z square. So let me first estimate it like this. And then I'll use a triangle inequality to say that 2z plus 2 in the absolute value is less or equal. Now, I know at least half of you will have questions, but I encourage you to rewatch this video slowly and see that I'm not messing the signs up. So that's the triangle inequality. This implies that minus the absolute value of 2z plus 2 is bigger or equal, because I have the minus now, than this. And so this implies that what I wanted to estimate is bigger or equal than this minus this. This is bigger or equal than z square minus 2z minus 2. And we are on this arc, on this semicircle, so this is r squared minus 2r minus 2. And that's all I need, because now I'll write length first, so I know that the length is pi r times the biggest value of f. And, well, r squared wins. R squared wins. So this will be it. So now we scroll back to this line. We imagine writing a limit here, a limit here, and a limit here. And this limit is what we need. This limit is 0, so goodbye. And this is still pi. So eventually the answer will be pi. So if we want to check it, then we need to write that x squared plus 2x plus 2 is x plus 1 square plus 1, so you complete the square. This you can check by hand. And so I'll just compute the antiderivative. Here I can compute the antiderivative. It will be this. Now I will make a u substitution. X plus 1 is equal to u. Dx is equal to du. So this is integral of du divided by u squared plus 1. This is tangent inverse. And u is x plus 1 plus c. C is not a contour now. C is a constant. And now I need to plug plus and minus infinity, so the limit of tangent inverse when x goes to infinity is pi over 2. The limit at minus infinity is minus pi over 2, so we'll get pi over 2 minus minus pi over 2, which is pi. So if you do this slowly, you will confirm the answer. Okay, so before we finish, and I'll send an email about it too, I'll tell that I'm very seriously thinking about surrendering to Zoom and to real-time lectures for various reasons. One of them is that I'm not really happy with nobody asking questions, so I'm not so much confident about my virtual teaching skills, so I think many of you do not like the speed at which I'm teaching when I don't see your faces. So we'll probably at least try switching to Zoom and see how it goes, but I'll still do the recordings and I'll still post them on YouTube. So like attendance won't be so necessary, but at least I'll have a chance to see the live chat and maybe your faces if you're willing to turn on the camera. So maybe we'll try to do Zoom next time. I didn't want to do it on Friday. I'll actually test it on my grad students who are less vulnerable. And if it goes fine, we will start Zooming on Monday. So have a great weekend, and please don't hesitate to use the discussions on Canvas. I think it's actually not such a bad substitution for office hours because uh, not only I can answer questions and we can all discuss them. And if you ask lots of questions on Canvas, then your fellow students will know that not only they are struggling, and that's good too. So please feel free to ask anything on Canvas. Well, have a good weekend.